Okay, then I'll try to speak in English. In the first part of my speech, there was a theme about double sine, and there were covered definitions of Bernoulli polynomials, multiple gamma functions, and there was a representation using integral of logarithm of multiple gamma function. After that, I said all general properties of double sine, which were defined using multiple gamma function in this way. Okay, I marked the most important of them as equations and used letter U1. Then we got identity of okay, and how to say it in English, тождество обращения using, and it will be under letters O1. Then we got integer shifts of arguments on omega 1 and omega 2. This formula are under letters and symbols plus or minus 1. Then we got information about zeros and poles of double sine. Yeah, and its residues in poles. And the last thing we got is a double sine of automorphisms. The first one is symmetry, and the second one is multiplication on non-negative or positive real constant of all of its three arguments. Yes, and now I would like to talk about Ruijsenaars' definition of hyperbolic gamma function, and I believe it will be time today for the third part, where I would like to get this definition from the first one. Okay, first of all, we consider an integral from 0 to infinity. And define in such way a function g of a plus, a minus, and z, where a plus and a minus are from the line from 0 to infinity. And we will write in such way a delta all of these two constants. For now, it will be their constants. Yeah. where delta from minus and plus. Okay, what can we notice? The first thing is that this integral have an absolute convergence on that belong in that belongs this strip. To check this, we have to look at a coefficient on a Taylor series on Z in 0 and on asymptotic on asymptotics of a function in this integral when z when y goes to infinity. Okay, in 0 we can see that there's no problem because if we look at the series in it, we can see that there are no coefficients on summons of the of the summons. Yes, there will be with the 0 coefficients. Let's check this. Okay, we have this representation of hyperbolic sine. Then, okay, and represent original sine. Okay, and then we can see that the coefficient of the lowest degree monomial is exactly the same as here. And then in sine we have summons of the form y squared and some coefficient or greater, or you have a great degree. That's why we don't have a problem with this degree. That's why in 0 everything is okay, and this permission is only follows from its properties or when y goes to infinity. Okay, we just can represent hyperbolic sine and original sine as two exponents, and then it easily follows that modulo of imaginary part of z have to be less than a plus a minus divided by 2 to be this thing convergent. Okay, then we define g big as exponent of ig small. Yeah, where g small is this integral. And then I would like to prove this identity. the author of this article proved this thing in more general case, and then just wanted to calculate this part using a general solution for equations of this type. And the main thing he wanted to notice to go to his general way of getting a solution is a thing that in this strip our function our big G function is analytic. But I don't want to show his ideas of his general solution, because this is a little bit different subject, and I wanted to find a way to prove this identity using some basic knowledges from math. But suddenly I noticed that my solution isn't work for all of that from strip. Okay, not for all of that, but it works for that from a real line. That's why I want to show you the ideas how to prove this using hands where that is real. Okay, first of all, we fix delta as plus. Of course, where delta is minus, there will be by symmetry an analogous thing. Okay, we can rewrite this as an exponent of I multiplied by to integral and here have sine divided by two hyperbolic sines
Второй раунд уже пошел.
Да, но я не буду слушать первый доклад.
and then we want to look at this integral. These two signs we can rewrite as multiplication of sine and cosine. Okay. Okay, and then we can get I from this sign and have a hyperbolic sign with the same argument as here. That's why we can get this integral. Let's name it as I0. Then we can notice that
Wait a minute, please. I would like to look once more at the last integral. It seems to me you have lost convergence.
mm, mm, mm. No, I think
No,
it
okay,
converges.
sorry,
Yeah,
sorry.
because we have a cosine.
Sorry, okay.
Then I want to look at integral of this form, where I put into my first integral instead of cosine of 2yz a sine with the same argument, because I get an odd function then. Yeah, I can oh no, not here. What I mean, I want to consider this thing. Here we have an odd function, and then I want to consider it from minus infinity to infinity in the meaning of principal value of its principal value, and then we know that this will be 0. Then I want to rewrite the first integral, because here we have an even function. I can rewrite it as an integral from minus infinity to infinity, and have a sum of it with j. Then a value of 2i0 exactly equals to I of this integral. Okay, then I would like to calculate it using Jourdain's lemma, and it is essential that that is real.
And now you have lost I in the exponent.
I have I here.
In the exponent, you have cosine.
Yeah, okay. Thank you. Okay. let's look to this argument of exponent. And let us fix the value of z as, for example, not negative. Then we can take this contour and we have to be careful because we have poles of hyperbolic sine on the imaginary line. That's why we will take a family of contours of this type where R is between is the mean point between two poles of hyperbolic sine going one after one. I mean, this is the first way of R, second, third, and etc. Then using then we have to look at the integral by this part of contour, and we can notice that this integral will be limit of these integrals of a part of a function where we have y squared in denominator will be 0, and by Jordan's lemma here we can choose a constant for hyperbolic sine because of the choice of these r's between its poles. It's 0, sorry, yeah. And then we can say that an integral without this y will be module of it will be less than some constant, and this y gives us convergence to 0 of the full integral. Okay, then we can calculate the value of I0 using residues of this function inside our contour. And what exactly we have to calculate then? We have to calculate residues of form omega, where omega is exactly the thing inside our integral. In zeros of hyperbolic sine. Okay. We can do this in 2 steps where k is not 0, and the second step where we have a residue in 0. Because here we have non-zero residue. And because we have here a simple pole in 0, that's why we can calculate this integral as a semi-residue. Okay, now I'll write down these values. will be of the form -1 in the power of k. And okay, and second value is then we have to calculate a value of this series, and here we get exactly natural logarithm of this thing. And this value gives us this summon. Yeah, and because of this I and this coefficient, we now just have to calculate an exponent of this value. And this will be exactly what we need. This is hyperbolic cosine with argument by z a minus. If we have negative values of z, then we just can to rewrite this contour and go to minus infinity on our imaginary line. Then for real z, we can by hands prove this identity. Let's call it E plus or minus, which depends on the sign of its A. As a corollary from it, we can get another identity of the form which can rewrite as and just using 2 times our identity E plus or E minus, we can get this. And this is exactly this to hyperbolic sines. Let us call it E2. Then we can see something about orthomorphy properties of our function. First of all, it is the symmetry of its two arguments, which is obvious. The second one is multiplication on a positive constant. Which follows as in the previous part exactly from integral representation of this function. But if we had to think to think careful about convergence of something to zero in the previous part. Now we don't have to do this because we don't have a logarithm, we have a meromorphic function. That's why we can easily do change of variables and get exactly this function. As for the third property, this is this, which is obviously follows from definition of G big. I mean, as a first step, we can put we can replace minus in our z argument to minus in front of this integral, and then we can use an exponential property. Okay, and now we have an interesting identity which has the following form. It have to be equal to this product it follows from definition of G big from using G small, and from this identity it tools in one step from considering this as geometrical progression, and how we want to apply it. We want to look at this integral where we have not a plus, for example, but a plus divided by m. And then using this identity, we want to replace a plus divided by m to just a plus. But we get exponents in, yeah, we get exponents here. And why they can go to the argument of the sine? This is so because we can represent sine as a sum of two exponents, and for this summons, apply this identity for hyperbolic sines, and get get another summand in our argument which we want to get. Yes, and one more thing we have to notice to do this correctly is this thing. We can replace y to minus y, and because of oddity of these two things, we have the same identity. Yes, that's why we can get easily from this identity the desired arguments in product. But what can we say about this summand? Why it will be all correct for it? This exactly follows from the things that sum of m plus 1 minus 2j, where j from 1 to m, we get 0. Okay, then we have this this identity in case where n or for example m equals, oh, I replaced two letters, where n equals to 1, and because of the symmetry of these two arguments, we can get it in this form for every m and n in natural numbers. Let us call it C. Okay, now I would like to study poles and zeros of G function. Okay. Okay, G big have this zeros and poles, and we can calculate its residues. For example, of residues of poles, residue in. Okay, let us redefine it as ZKL minus and ZKL plus. Then we want to calculate the residues of all of them. And the first statement is that the residue of Z0 is exactly and residue of ZKL general is minus 1 to the power this. Divided by product of sines and sines. Okay. Let us call this thing as Z2. This is E2. This is R2. How can we get it? The main idea which it follows from is this form. Let us take G with this argument and apply to it E1, E1 plus, E plus, okay, M times. Then we can rewrite it as G of Z multiplied, divided by this product of hyperbolic cosines. Yeah, and before it, we can consider that A plus is less or equal than A minus. Yeah, then we take this representation, and we can notice that we can have poles only in points of the form that L, which are defined as plus M minus this. where m can be 1 to m, and L is integer. First of all, we know that in our strip S we have no poles and zeros. That's why if we can choose for each m and L, which are of course integers, so such m big as an argument z will be in this strip S, we will get that there is no poles except the zeros of our hyperbolic cosines, which can get for big m's. Yeah, I mean all of them, which we can get. To say it formally, first of all, if we fix m and m big, then we can take a unique L which is not less than 0, such that an argument z will be in our strip. Then we know that this ZMN is a pole. What is about now all the coefficients from natural numbers? Okay, for first of all, we want to notice that if we subtract from this ZML our imaginary part of MA plus, we get here a negative coefficient which is related to A plus. That's why we want to cover all of the natural numbers with zeros. And if we can prove that for all of these numbers we have poles, this will be the end of the proof, the statement about poles. Okay. Of course, for every natural numbers m and L, we have such big m big as for this sum we can go inside our strip. This is so because A minus is not less than A plus. Then we can go choosing different m big. Yeah, we can go as close as we want to. So now we know that all the poles are of the form P2. And then easily we can get all the zeros of G big. We want to use the property number 4. Let us call it A4. Oh, sorry, not 4. A3. And get all of the zeros. What about residues in poles? First, we want to calculate the residue in the pole with coefficient 0, 0. We want to consider this thing. this is an identity E2. E plus, sorry, yes. In which we changed our argument. Okay, and we get this equals to hyperbolic sines of this argument multiplied by this thing. Yeah, we just want we just have to replace our argument in E plus from z to z minus a half of I a minus. Okay. Then we know that if we take a limit when z goes to 0, we will get a point which are in the strip there. Okay, but here we cannot say the same. Yes. Okay. That's why we can calculate a residue of this thing in 0. This will be exactly this value. Oh, sorry. Multiplied by this. Okay. We can do exactly the same for inequality E minus. And then we can get that this also equals to I a plus divided by 2p and minus a plus. Okay, and then we want to use one more time our orthomorphism property number 3. And get that this value in square equals to plus or minus. Then to understand what sine will be here, we can notice that we have an integral of pure imaginary number. That's why we will get exactly a positive number because we have an exponent. Oh no, yeah, because we have in the argument of our exponent another I. Yeah, that's why g of the same argument is square root of, which is a real square root. And then R00 equals to this. Okay. Yeah. Then we want to do the same thing, just and just we have to rewrite this argument as an argument. Rewrite it in such way that here we will get an argument z plus z00 for we can calculate this residual. Okay, and we'll get the following thing. Yeah, of course, using e plus once more and a minus. Okay. Then taking a limit, we can get what desired. Exactly this thing. And of course, I want to notice that this thing can be 0 exactly when a minus divided by a plus is a rational number. That's why we can calculate it in the case when a plus divided by a minus is irrational. Okay, then I would like to get a Ruijsenaars representation from the first one. To do this, first of all, I have to notice the thing. I can define this function as follows. Okay, and if I write it in the terms of double sine, it is exactly the double sine with an argument the following form. Now, what can we say about this function? First of all, it is an analytic function where when real part of z is less than this real part. And we want to look at equation, which is similar to equation for else. Okay, it follows exactly from the properties of double sine. Yeah. from okay. From this property. Now we want to consider function g with a hat, where we change once again an argument in double sine. This will be a double sine with this argument. Now we have a permission that imaginary part of that have to be less than semi-half of sum of a real part of 2 omegas, and we want to check that this is exactly a Ruijsenaars case. Okay, first of all, we can see that we have this, the same one equation as Ruijsenaars was here. And what can we say about its integral representation? Okay, to end with, I would like to how to get from the first integral representation the desired one. Okay. Our first representation has a form and of course there have to be logarithm. Can remind that C is the contour of this form. That's why here we can rewrite this as a limit of these 3 integrals. Here, nothing changes except logarithms. We have here yeah, we rewrite this minus as the following in the following form to get a continuous of our logarithm. Then we can do the same thing for the bottom part of our contour and get here a logarithm with this exponent. And the third summand is an integral over circle, in which we can rewrite as okay. Okay, and I was part. Okay. Here in these two summons, we can notice that parts with logarithm of t will be killed, and from the parts of an argument of exponent, we will get 2 pi. Okay, then we can rewrite this thing as this limit. Yeah, okay. Nothing was changed here, but we divide onto 2 pi I in denominator. That's why we don't have this coefficient, because we had 2 pi I from these two. And the second sum is okay, has the following form. This is okay. Why is it so? Because we can rewrite it as a series n0 on epsilon. Oh, yeah, and get what we want to. Then we have to calculate this integral, and we can notice that because of the fact that we take a limit where epsilon goes to 0, this part of our sum will give us 0. And the first part with 1 can give us here it can give us 0. But here we can have non-zero thing. Okay, then it equals to this limit. And this thing. Then we can rewrite this thing as an integral of 1 divided by 2 squared. And as a result, we get we can get an integral from 0 to infinity. Okay, I was a following. Okay, and if we replace that minus by z hat, we will get the Ruijsenaars definition of a hyperbolic sine. Sorry, hyperbolic
Double sine.
Yeah. Okay. I think that's it. So to end with, I can say that in the first part we considered one way to define to double sine. In the second part, we looked at Ruijsenaars' definition of it, and we got similar properties of it using different techniques. And in the third part, we just got a union between the first definition and the second one. So I think this is the end.
And your Ruijsenaars definition is just the integral representation you have written in the beginning.
Yes. Yeah, this is him definition. His definition.
Okay. So you just showed us that this integral, well, this function given by integral representation satisfies all the properties that you listed previously.
Yeah. Yes. But first of all, I showed that this can be done autonomously. And then I just showed that this integral is a special case of more general thing.
Okay, I see.
Ага, так.